Hello everyone, welcome to IGNOU Dost. So in this today's lecture, we'll be starting to learn about introduction to matrices. Okay, so we'll learn about what are all different type of matrices that are there. We'll understand the operations on them. We'll understand what could be the multiplication of a matrix. What does it mean when you're trying to multiply a matrix with a scalar, and a lot of other things that are completely related to matrices, right? And we'll also understand the meaning of a matrix, where we're going to use it, and the several operations possible on it. So we'll see a brief picture, and this will be the part one of the concepts of introduction to matrix, right? So we'll jump into the very first segment of the matrices. Matrix, or we would say matrices in plural, right? So if you're using multiple multiple number of matrix, then we term it as matrices. Is an arrangement of numbers into rows and columns, right? So it is an arrangement of numbers in rows and in columns. So basics of it, because of its features of compact notation for describing sets of data and efficient methods for manipulating data sets, it becomes a handy tool for finding solutions to problems which can be represented in linear equation system. So let us assume there are two equations, a1x plus b1y plus c1 equal to 0, and a2x plus b2y plus c2 equal to 0. So if you're trying to evaluate the solutions for these two equations, right? So if you're trying to find the solutions to these two equations, then you can take the help of matrix. So we'll see several methods that are involved with the matrix, and what are all its applications. Right? So needless to say, matrix algebra finds wide applications covering the fields such as engineering, economics, and business, sociology, statistics, physics, medicine, and information technology. Right. So we use matrix in the field of ML. Right. So it is a basis of linear algebra, and that is indeed again the basis of ML. So there are a lot of linkages. There are a lot of inclusions of matrix. There are many areas in which matrix is deeply, this used. So we'll see how are we going to use matrix and the perfect applications and types of matrix, everything related to matrix in the further step. Okay. So for a better understanding of the applications, consider the following examples. So socialists use matrices to study the dominance within a group. Demographers use these to study births and survivors. And industries and businesses take the help of matrices for fast and accurate in decision making in the areas like evaluation of customer preferences to produce and sell. Right. So there are many vast areas. So matrix like represents a lot of things. For example, let us assume you are what you and your five friends are there, right? Let the five friends name be A, B, C, D, E. And there are movies that are, let us assume the name of the movies are L, M, N, O, P, Q. Okay. A watches L, right? A watches M, but A doesn't watch N, doesn't watch O, did not watch O yet, did not watch P yet, did not watch Q yet. Okay. So these are the names of these movies, and these are the names of the friends, right? So A watched the movie L, A watched the movie M, but did not watch N, did not watch O, did not watch P, did not watch Q. B watched N, B watched M, B watched N, but did not see O, did not see P, did not see Q. Similarly, C watched N, but it did not watch L, M, and N, but watched P, but watched Q, O, but watched P, but did not watch Q. Coming to D, it watched all of the films, okay? And coming to E, it did not watch any of the films. Now, if you carefully observe, right, if you carefully observe, A and B are somewhat closely related, right? Because B watched three films and A watched two films. So the particular OTT, or you would say, let us take example of Netflix or Amazon Prime, whatever it is, it will try to recommend A the movie N, right? So it will try to recommend the recommendation systems of that particular application will try to recommend N as the next film to A to watch, right? Because B watched all of these films, right? B watched all of these films. So, and A watched L and M, but N it did not watch it. So the recommendation system will try to analyze that someone that is close to A, that is B, we watched three films. So let us recommend the next film to A. That is how the system behaves, right? So this is all a pure application. These are all pure applications of matrices, right? So this is how it is helpful. So this is not just the only field where you see the application of matrix. That there are various others as well. So that you can do on your own research, get to know what is actually happening. So some use linear programming techniques that is based on matrix formulations of data to maximize profit and thus plan production or availability of raw materials, right? So this is also very, very helpful in business. So there might be a case where you wanted to decide whether a product must be manufactured at a larger scale or at a small level, small scale, so that you can only estimate that with the help of the demand, right? So if a particular product is in high demand, then you would definitely want to manufacture that product in a large scale. But if it's not, you would definitely manufacture that at a small scale initially, and then try to see if the demand for it is increasing. So these are all things dependent upon, these all things are all dependent upon matrix at the end of the day, right? So economics use matrices to examine inter-industry flows for studying game theory and to construct the system of social accounting. So moreover, in medical studies, scientists use data in matrix form to determine a statistically valid rate of efficacy of a drug before prescribing it in hospitals and pharmacies, right? So even matrices are helpful in that in the pharmacy domain as well, in the biotechnology domain as well. So if you wanted to test whether a particular medicine is being helpful or it is having any sort of side effect, or is it really going to help the people at a large scale, everything can be determined with the help of matrices, right? Matrices are like the purest form of elements that could help you to decide many things, and that are especially dealt in a large scale, at a large scale, right? So I hope you people understood. So what is the definition of a matrix? So a matrix is defined as a rectangular array of numbers arranged in rows and columns enclosed by a pair of brackets. That is square brackets like that, or open brackets. For example, the following array of numbers shows in a matrix as this, right? So this is a matrix where you could see 11, 42, 22, 84, 10, 15, 60, 25, 41, 28, 45, 51. All these are numbers, right? So these are arranged in horizontal rows and vertical. So on the basis of number of rows and columns that a matrix has, we can decide its dimension or its order. By convention, rows are expressed first and while columns are expressed in second in the matrix. So what do they mean? So let us take the example in the previous case itself. So the matrix that we have taken. So since the above matrix has three rows, right? So we have three rows. What are those rows here? So this is row 1, this is row 2, this is row 3, right? Rows are always horizontal, right? Rows are always horizontal. So you can remember like that. And columns are always vertical, right? Columns are always vertical. So how many rows are there here? Three rows are there. How many columns are there? Four columns are there. C1, C2, C3, C4, right? So there are rows, three rows. How many rows are there here? Three rows and four columns, right? So the order of this matrix is denoted by 3 by 4. So this is the order or the dimension of that particular matrix. So if I give you this matrix and I ask you to tell me what is the order or the dimension of that matrix, you would say the number of rows by the number of columns. So we have three number of rows by four number of columns, right? So I hope you people have understood. That is how you determine the dimension and rows of a particular matrix. I mean, order of the particular matrix. So a matrix is usually denoted by a capital letter and its elements by corresponding small letters with two subscripts, which indicate the row number and the column number. For example, an element represented as A23 in a matrix is read as to its position in second row and third column. Okay, it's not A23 to be honest, it's A23. Okay, so thus a matrix having m rows and n columns can be written as this. So this means A11, that means it is the first element, first row, first column. Okay, the element that is present in first row, first column. A2n. So what does this mean? Second row, nth column. Okay, so the element that is there in the second row, nth column is A2n, right? So that is what it it means, right? I hope you people are able to understand. So first write the row at which it's present and then write the column at which it's present. So the above matrix can be written as A equal to Aij, right? So Aij and M by N, where I equal to 1 to 3 so on till M and J equal to 1 to 3 so on till M. Why I is equal to 1 to 3 so on to M? Because there are M rows, right? So from this you could see the last element is telling that it is on mth row, right? It is on mth row and nth column. That means that is the last element. So what can you say that this particular matrix A is having M rows and n columns. Okay, so that is the reason I is the number of rows here because I is starting, and we said what is the starting one? It is denotes the number of rows. And what is the second one? J, that is columns. Okay, so this is columns. This is columns. So and we saw that here it has n columns, so it goes up to n. Okay? So that is how you interpret a matrix, right? I hope you people are able to understand. Very, very easy concepts, nothing complex here. So coming to the type of matrix, okay? Type of matrices. So first type of matrix is rows matrix. So a matrix which has only one row or a matrix of order 1 by n is called a row matrix, right? So this is a row matrix here. Why? What are the number of rows you have here? Only one row. Okay, we have only one row. How many columns we have here? Three columns. Okay, so this is also a row matrix, right? Because it has only one row and two columns. This is also a row matrix, -3, -2, -1, 0, 1, 2. Because there are how many columns? 6 columns in total, right? 6 columns in total. And how many rows? Only one row. So if this is a case where there is only one row and number of columns is not fixed, like it could be n number of rows, then it is known as row matrix. Right? So I hope you people are able to understand. Then what is a column matrix? A matrix which has only one column, or a matrix of order m by 1, right? So in this case, you can have multiple rows, right? Multiple rows, but only single column, right? But only single column. Then it is known as column matrix. Right? I hope you people are able to understand. That's it. Row matrix in the sense only one row. Column matrix in the sense only one column. Okay, and the other one could be multiple. There is no dependency on that particular. So these are the two type of matrices. Coming to the third one, rectangular matrix. So what is a rectangular matrix? So yeah, what is a rectangular matrix? So the rectangular matrix in the sense a matrix is said to be rectangular if the number of rows is not equal to the number of columns. Okay. So if you take the first example, in this case, here we have 3 rows and we have 4 columns. 3 is not equal to 4, isn't it? So it is a rectangular matrix. And come to the second case. We have 3 rows and 2 columns. 3 is not equal to 2. So therefore it is also a rectangular matrix. Now what is a square matrix? A matrix in which the number of rows is equal to the number of columns is called square matrix, right? So if you take this example, you have 4 rows and you have 4 columns, right? So your m, that is the number of rows, is actually equal to the number of columns. So this is termed as square matrix. So that's it. There is no much difference between a rectangular and square, only that in your square matrix, the number of rows is equal to the number of columns, and in rectangular matrix, your number of rows is not equal to the number of columns. That's it. Come to the next one. Diagonal matrix, right? So a square matrix in which all the elements except the diagonal elements are 0 is called diagonal matrix. Okay, so a square matrix in the sense we have already discussed, in which number of rows is equal to number of columns, in which all the elements except the diagonal elements are 0 is called diagonal matrix. Square matrix Aij is a diagonal matrix if Aij equal to 0 for all I not equal to 0. Okay, so very, very careful to observe. What are they saying? For all I, okay, for all I not equal to j, Aij equal to 0. So if you consider this is not equal to 0, right? Why is it not equal to 0? Because what is the position row of this particular element? 1. What is the column of this particular element? 1. So 1 equal to 1, right? So in this case, your I equal to j. So that is the reason it is not 0. Okay. But if you come to this, okay, this is first row, second column. Okay. So here your I equal to 1, j equal to 2. Your I is not equal to j, right? If I equal to not equal to j, then your Aij must be equal to 0. That is the reason it is 0. Okay. So this is the diagonal matrix. So in a diagonal matrix, your Aij, right? Your Aij, the element at the ith row jth column will be 0 if the I is not equal to j. Okay, that is the basic. So, or in the easier terms, you can remember that in the diagonal, all the elements will be non-zero, and in the non-diagonal, okay, all the elements will be 0. That's it. Very easy to remember. Coming to the next one, scalar matrix. A diagonal matrix in which all the diagonal elements are the same is called scalar matrix. Okay. Now that you understood the diagonal matrix, scalar matrix is just an extension of the diagonal matrix, right? In scalar matrix, all the diagonal elements would be the same. That's it. That's the only difference between a diagonal matrix and a scalar matrix. So coming to the next matrix, that is identity matrix. So a scalar matrix in which all the diagonal elements are one is called unit matrix, right? So this is an extension, right? So first you have seen diagonal matrix, right? From this you have got scalar matrix, right? From this you have got scalar matrix, and from scalar matrix you got identity matrix. You got identity matrix. So here all non-diagonal elements, or I would say yes, all non-diagonal elements is a perfect thing to use. All non-diagonal elements are 0, right? And in this, all diagonal elements are same, right? And here, all diagonal elements are 1, right? So that's the only thing. This is an extension of from diagonal matrix to scalar matrix, from that to identity matrix. Okay, I hope you people have understood. Now coming to the next thing, triangular matrix. What is a triangular matrix? A square matrix is said to be triangular if all of its elements above the main diagonal are 0, lower rectangular matrix, or all of its upper elements below the main diagonal are 0. Okay, so above the main diagonal are 0 or below the main diagonal are 0. So we'll see that now. How is it? How does it look? So for example, if you see this example 1 and 2 and 1 and 2, so here you can see that in this case all the elements to the upper side of the diagonal element, right? So this is the diagonal thing, and all the elements to the upper of it, including the diagonal, are non-zero. But all the elements below it are 0. These are all 0, isn't it? 0. So this is known as upper triangular matrix, right? So your upper triangle matrix, in the sense, with the name itself, you can say that all the elements upper to the or to the right side, or you would say to the upper side of the diagonal thing, are non-zero. Okay, then it's known as upper triangular matrix. But when it comes to lower triangle, the opposite. So lower in the sense, including the diagonal, whatever the elements that are there to the lower side of the diagonal, all of them should be non-zero, and the upper side, all of them should be 0. That's it. If this is the case, then we can say that this is a lower triangular matrix, right? So I hope you people have understood this thing. Now coming to the next one, what is null or zero matrix? So a square matrix is in which all the elements. So it's important to note it is a square matrix. Okay, it is a square matrix in which all the elements are 0. Okay, and then it is called zero matrix or null matrix. So it is denoted by capital letter O. So this is how it is. So this is a zero matrix, right? Because every element in this matrix is 0, and also it is a square matrix. What is a square matrix? Your number of rows M.E should be equal to, right? In this case, it is 4 equal to 4. What is a symmetric matrix? Square matrix A equal to Aij is a symmetric matrix if Aij equal to Aji for all I and j. We will revisit this matrix after covering the transpose of the matrix in this unit. Okay, there's another concept called transpose. We'll see that later. But what is a symmetric matrix? Symmetric matrix in the sense your Aij should be equal to Aji. So for example, take this scenario. Okay, so what is this is A11. Okay, sorry, yes, this is A11, and this will be equal to A11 itself, right? Because it's all it's the same thing. I equal to 1 and j equal to 1. Come to this. Okay, here I equal to 1, j equal to 2. Now according to the symmetric matrix, A12 should be equal to A21. What is 21? Second row, first column. So that is this, right? You can see that both of them are equal, right? Now take this. This is I equal to 1, j equal to 3, right? First row, third column. According to the symmetric matrix, A13 should be equal to A31. So this 5 is actually equal to this, right? So both of them are equal. So this is how it goes, right? So these one also are equal, this is also equal, this is also. So symmetric matrix in the sense Aij should be equal to Aj. If that is the case, then it is a symmetric matrix. Okay. I hope you people have understood this thing. Very, very easy concept. There is nothing difficult in this. Very simple definitions. Coming to the next concept, submatrix. So a matrix obtained by deleting some rows or columns or both of a given matrix is called submatrix of the given matrix. So for example, you can see that if I assume this is the total matrix, and if I delete the first row and the first column, I would get this matrix, right? So this is a submatrix. Very simple. If you delete a particular row or a column, then it would be a submatrix. What is the trace of a matrix? The sum of all diagonal elements of a square matrix is called the trace of a matrix. Remember, it should be a square matrix, and the sum of all elements in the diagonal. Okay, so 2, 3, 4. What is the trace of this particular matrix? Trace of A, that will be 2 plus 3 plus 4. That is actually equal to 9. Okay, so and it is denoted by TR of. So trace of A is basically the sum of all the elements present in the diagonal. Okay, so that is how uh, you get the trace of a particular matrix, right? So now to the next concept. Now that we have seen different type of matrices, we have understood what could be what are the properties, and we have seen different classifications possible. Now we'll see the matrix algebra. That means operations on this particular matrices. Right? So in this section, we'll discuss the basic operations of matrices. We start with the idea of matrix equality before taking up the operations of addition and multiplication. Right? So there's a concept of matrix equality, very easy. We'll discuss that first, and then we'll jump to the addition and multiplication. In matrix algebra, the elements are ordered numbers, and therefore operations on them have to be done in ordered manner. Okay, so the elements are ordered numbers, and therefore, so everything has an order. It's not that you do some random operations. You have to follow an order. It may be useful to note that while we deal with the main operations such as addition and multiplication, other operations such as subtraction and division are derived out of those. Right? We'll see all of this in great detail. So, as said, what is the equality of matrix? What is the concept? So, two matrices are equal if the following three conditions are met. Right? So, if I give you a matrix A and if I give you another matrix B, and if I ask you to tell whether both of them are equal or not, you need to check these three conditions. What are those three conditions? Each matrix has the same number of rows. Each matrix has the same number of columns. Corresponding elements within each matrix are equal. So if the above conditions simply require that matrices must under consideration are exactly the same. So if I take an example, so let us assume this example I've given you. Okay, I've given you A equal to 2x y3 and B equal to 2, 3, 4. And I said that A equal to B. So when I say equal to B, number of rows here should be equal to the number of rows here. Is it the case? If you see, there are 2 rows here. There are 2 rows here. Yes, it is. That first condition is done. What is the second condition? Columns should be equal to the number of columns. What are the number of columns here? 2 columns. Here also number of columns is. That second condition is also satisfied. Now, corresponding elements must be the same. That means A11, okay, A11 should be equal to B11, right? So 2 equal to 2. Okay, that is fine. Now come to X. X should be equal to 3. Then only B, A and B will be the same. Okay. Coming to Y. Y should be equal to 4. Okay. Y should be equal to 4. And 3 is already equal to 3, as you can see. Right. So from this, we can say that your X value will be equal to 3, Y value equal to 4. Then only the matrix X will be equal. If not, the matrices will not be. I hope you people have understood this thing. So only three conditions are there. Very simple. Rows should be the number of rows should be the same, the number of columns should be the same, and the corresponding element must be the same. Further, suppose that we are given a matrix as follows, like C equal to R S T X Y Z, then C is neither equal to A nor equal to B, as C has 3 columns, isn't it? So in A we have 2 columns, in B we have 2 columns. So if you're trying to compare C with A or C with B, your C should also have the number of rows and number of columns to be equal to A or B, right? But in this case, you have in C, you have 3 columns. So you cannot compare matrix C with A and B. C will never be equal to A. Okay. I hope you people have understood. Come to the next concept. Now comes the important concept, addition and subtraction of two matrices. So matrices can be added or subtracted if and only if they are of the same order, right? So order, we have already seen what is an order. Order is the number of rows by number of columns. So if I give you a matrix A and if I give you a matrix B, and if I ask you to add the matrix A and matrix B, you need to make sure the number of rows and number of columns in A is equal to the number of rows and number of columns in the B. Okay, then only you can add the two matrices. Not you cannot add. So the sum of difference of two M by N matrices is another M by N matrix whose elements are the sum or differences of the corresponding elements of the given matrix. Right. So we'll see that in using examples. So for two matrices A equal to Aij M by N and B equal to Bij M by N, A plus B equal to C or A minus B equal to C. So if the third matrix is the addition of these two matrices or subtraction of these two matrices would be the corresponding elements, okay, applying the operation on the corresponding elements. So for example, take this example, right? So we have, 0, 7. When you add them, you get 7 as the final answer, right? You get 7 as the final answer. We have 2 and 3. 2 plus 3 equal to 5. 3 and 5. 3 plus 5 equal to 8. 2 and 5. 2 plus 5 equal to 7. 1 and minus 1. 1 plus 1 equal to 0. 4 minus 3. 4 plus minus 3 equal to 1, right? So this is how we will find the corresponding matrix. So it's important to observe A is 3 by 3 and B is also 3 by 3. That is the reason we are able to add it. If there are different orders, we will not be able to add. Similarly, this is A plus B. A minus B is also similar. So 0 minus 7 minus 7. 2 minus 3 minus 1. 3 minus 5 minus 2 minus 5 minus 3. 1 minus 1 minus of minus 1 2. 4 minus of minus 3 7, right? So this is the value of A minus 3. So it's again important to note that the order should be the same. Okay, the order should be the same to apply the operation. If not, you cannot apply the operation. Very, very important point, right? So I hope you people have understood. Coming to the next concept, negation of a matrix. The negation of a matrix A is denoted by hyphen A, or you can say negotiation of A, which is obtained by replacing all the elements of A by the negation. For example, if A equal to 1, 3, 5, 5 minus 1 minus 1, the negation of A would be just multiply minus 1 to all the elements of that particular A. So minus 1 into 1, minus 1. Minus 1 into 3, minus 3. Minus 1 into 5, minus 5. Minus 1 into 5, minus 5. Minus 1 into minus 1, 1. Minus 1 into minus 1, 1. That's it. That's how you'll find the negation of a matrix. So the subtraction of two matrices A and B can be expressed as a sum of A and the negation of matrix B, right? So A minus of B can be written as A plus of minus B, right? And we have seen the addition of two matrices in the previous slide, and minus B is just a negation of B. Okay, negation of B. And how do you find the negation of B? Just multiply minus 1 to all the elements. That's it. And then you'll add them to find A minus B value, right? I hope you people have understood. That is the reason we studied the concept of negation. Okay, negation is just that you multiply minus 1 to all elements of that particular matrix. So coming to the next concept, multiplication of a matrix by a scalar quantity. If a matrix is multiplied by a scalar quantity, then all the elements are multiplied by that quantity. Okay, so if a matrix A equal to Aij m by n is multiplied by some scalar quantity k, then k times A is basically k times Aij m by n, and that is k times Aij m by n, right? We'll see that in brief. Okay, or if you want me to take an example, let us assume there is a matrix 1, 2, 3, 4, and I said k equal to 3. That means multiply. So this is A. Okay, this is A. Then k times A is basically nothing but multiply k with all elements of k. So 3 times 1 is 3. 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12. So this is the value of k. That's it. We just multiply k with all the elements of A to get that particular k times A matrix. Right? Now some of the properties of scalar multiplication are like if there are two matrices and two scalars A and L. So k times A of B will be Ka plus Kb. K plus L of A is equal to Ka plus La. KL times A equal to K times La is equal to L times Ka. Minus Ka times is equal to minus of Ka is equal to K times minus A. 1 into A equal to A, minus 1 into A equal to minus, right? Very, very simple. Very, very obvious things. You can try doing on your own. You'll be able to derive all of those. Come to the next thing. Properties of addition of matrices. So addition of matrices is cumulative. That is, if A and B are two matrices of same order, then doing the operation A plus B is same as doing the operation B. Okay. Addition of matrices is associative. So for the first one, if you want me to take an example, so take an example 1, 2, 3, 4 as the one matrix and 7, 9, 10, 12. Okay. So what do you get if you add both of this? 7 plus 1, 8, 9 plus 2, 11, 3 plus 10, 13, 12 plus 4, 16, right? So if I add them like this, 7, 9, 10, 12 plus 1, 2, 3, 4. So I would get the same thing, 7 plus 1, 8, 2 plus 9, 11, 10 plus 3, 13, 12 plus 4, 16, right? So I've got the same values, isn't it? So that's it. So these are like accumulative. So commutative. So A plus B should be equal to A B plus. That's coming to the next one. Addition of matrices is associative. Like if there are three matrices A, B, C of the same order, then A plus B plus C should be equal to A plus B plus C. Okay. Existence of additive identity. So if A is a matrix and O is a null vector of the same order as of that of A, then A plus 0 will be equal to 0 plus A equal to A, right? So if I take a matrix like this, 1, 2, 3, 4, so plus 0, 0, 0, 0 will be equal to 1, 2, 3, 4. So the additive identity is basically that matrix upon which if you add to the original matrix that you have taken, let us assume this is A, you will get the same matrix, right? So A plus O is giving me the same matrix A, right? So therefore this is additive identity. Now, what is existence of additive inverse? For any matrix A plus of minus A will be equal to minus A plus A, that is equal to 0. So if I take A equal to 1, 2, 3, 4, right? 1, 2, 3, 4, Then minus A, that is negotiation of A. That is -1, -2, -3, -1. Now what do you get if you add both of them? You get 0, 0, 0, 0. So this is additive inverse, right? So additive inverse is that matrix to which if you add your original matrix, you would get a null matrix. Okay, so this is a null matrix, right? So this is the additive inverse. Additive inverse is basically the negotiation or sorry, negation of the matrix that you have taken. That's it. So it's very simple, nothing complex in this case. So take the following example, right? Whatever the properties we have discussed, we can apply on them. So A equal to 1, 3, 5, 5 minus 1 minus 1, B equal to 1, 5, 1, 3, 6 minus 1, 2, C equal to 6, 1 minus 7 minus 2, 0, 5, and O, that is null matrix, that is 0, 0, 0, 0, 0, 0. Then A plus B will be equal to 1 plus 5, that is 6, and 3 plus 1, 4, 5 plus 3, 8, 5 plus 6, 11, minus 1, minus 1, minus 2, minus 1 plus 2, minus 1, right? So it goes on like this. You can see several operations we have made: A plus B, B plus A plus B plus C, B plus A plus B plus C. A lot of operations we have made, isn't it? So you can try doing them, you will get all of them verified. Okay, so very, very simple. So I hope you people have understood. So with this, we have ended the first part of this particular thing, introduction to the matrices. So we have covered a lot of things related to vector addition, sorry, matrix additions. We have covered a lot of things related to matrix multiplication with the help of a scalar. So, and we have understood the basic definition of a matrix, right? So I hope you people have understood all these things. So thank you for watching. Stay tuned.